So today's lesson, we're going to work on quadratic equations. This is chapter 15 out of the book. So we're going to cover sections 1 through 3. I think in your homework, you're just required to do 2 and 3, but 1 kind of is a good lead into 2. So when it comes to quadratic equations, the first thing we need to recognize is what's called the standard form of a quadratic equation. Ax squared plus bx plus c is equal to 0 is called standard form, where a, b, and c are going to be real numbers, and a has to be greater than 0. So what they're getting at here is there's these 3 terms. We have the ax squared. That's going to be called the quadratic term, as we mentioned earlier sections. So this is the quadratic term. It has to be present for there to be a quadratic equation. So the x squared term must be present. The other 2 terms are optional. So this is the linear term. Sometimes it's present, sometimes it's not. And then the c is described as the constant. It's just going to be a number. So one thing that's important as we move into chapter 15 is arranging quadratic equations in standard form. So if we have this 3x squared minus 3 plus 5x equals 0, that's not in standard form. So this 3x squared minus 3 plus 5x is equal to 0. The quadratic term has to come first, but notice how the constant and linear term, they're not in the correct positions. So the -3 and the 5 have to switch places. So all I got to do is rearrange this thing. So this just becomes 3x squared plus 5x minus 3 is equal to 0. And that would be the standard form. So minus 3 is equal to 0. Okay. So if I look at B, we have this 7x minus 2x squared minus 8 is equal to 0. So again, if we rearrange these, we have a -2x squared. The quadratic term has to go first. The 7x, the linear term, has to go second. And the constant, the minus 8, has to go last. And that would be what we call standard form. So if we have 12 equals 7x squared minus 4x, a lot of times what I like to do here is I like to switch the sides of the equation. So the 7x squared minus 4x, I'd rather have it on the left side, and the 12, we'll just swap rows there. So 7x squared minus 4x is equal to 12 would be the move there that I would make, is just swap the sides of the equation. Now, there's a couple of things we can do. The key is the quadratic equation's got to be equal to 0. So this 12 cannot be over here. So one way of doing it is we can just subtract 12 on both sides to get the 0 there and get the quadratic term and the linear term and the constant on the same side of the equation. So I draw the line here to bring down my new equation. So the quadratic term comes down. The linear term is the -4x, and the -12 is, like I said, it's not a like term, so it just comes down as well. And you'd have that as your standard form of the equation. That's me. So let's look at D. 7x squared equals 3. Another thing you can do is move things to other sides of the equation. When you move things to their side of the equation, in other words, their side of the equal sign, what happens is that term has to change signs. So if I look at this example here, notice I really want the 3 on the same side as the quadratic term. So what I'm allowed to do is just move it over, swap sides, if you will. But when I do that, the 3 turns into a -3, and that now is equal to 0 since there's nothing left over there. Remember, an equation has to have a right side and a left side. If there's nothing on that side of the equation, you use 0 as a placeholder there. So that would be what we call standard form. So some other vocabulary words that we're going to be coming across is there's this word complete quadratic equation. There's what's called an incomplete quadratic equation, and there's what's called a pure quadratic equation. So when it comes to a complete quadratic equation, it has all 3 terms are present. So the quadratic term, the linear term, and the constant are present. So that's a complete quadratic when all three terms are present. A quadratic equation that has just the quadratic term and the linear term, but there's not a constant present, sometimes that's called an incomplete quadratic equation. So notice that if you have the quadratic term and linear term present, this is described as an incomplete quadratic equation. And then this last one, a quadratic equation is some that has the quadratic term and the constant, but there's no linear term. This is described as a pure quadratic equation. So if the quadratic term and the constant are present, this is referred to as a pure quadratic equation. So it's helpful to actually give these three types of quadratic equations names as we move forward. So let's take a moment and see if we can write these equations in standard form. Also, we want to identify the A, the B, and the C in these examples. So remember, standard form, we have to have this ax squared plus bx plus c is equal to 0. So it's got to be in that form. So the a is the coefficient of the quadratic term, the b is the coefficient of the linear term, and the c is the constant. So we have to identify a, b, and c as we move forward. So let's look at example A. We have 3x squared plus 5x minus 2 is equal to 0. Notice how all three terms are present, so it's in standard form. So I got to identify as the a, which is the coefficient of the x squared, which is the 3. The b is the coefficient of x, which is the 5. And the c is the constant, which is the -2. So if I look at b, we have 5x squared equals 2x minus 3. So notice how it's not in standard form. The 2x and the -3 are not on the same side of the equation as the quadratic equation. So what we do is we just kind of move them over to the same side, which means they have to change sign. So that's 5x squared. This 2x turns into a minus 2x, and this -3 turns into a positive 3. And that's now equal to 0. So now I'm going to identify the coefficients. A is 5, B is -2, and then the constant is going to be the 3. So the C is going to be the 3. So look at C, we have this 3x equals 5x squared. So again, I really would like to have the quadratic term on the left side, so 5x squared is equal to 3x. Switch those around, but then I want the linear term on the same side of the equation as the quadratic term. So 5x squared minus 3x is equal to 0. So notice how the quadratic term is present, the linear term is present, but the constant is not present. That means it actually was a 0, because we usually don't write plus 0 down. But the constant is a 0 if it's not present. So then we can identify that the a is going to be a 5, the b is going to equal a -3, and since there wasn't a constant, it's actually a 0. So looking at D, we have -6x squared plus 2x is equal to 0. Notice how that's already in standard form. So a is the coefficient of the x squared, which is the -6. The b is the 2. And notice that there's not a c, so it's going to be 0. The constant is going to be 0. If I look at E, we have a 5x to the 4th minus 4 is equal to 0. Notice how, again, it's in standard form. But notice how the linear term is missing. So what we have is 5x squared plus 0x minus 4 is equal to 0. Since there's not a linear term, that means its coefficient had to be a 0. Because we don't write down 0x, it's just kind of dropped out of the problem. So what we pick up on then is our a is actually a 5, our b is actually a 0, and our c is a -4. So here we have x squared equals 9. So again, we can subtract the 9 to both sides, or just move the 9 over. X squared is equal minus 9 is equal to 0. Notice that the coefficient of x squared is actually a 1 here. There's not a linear term, so that means its coefficient was a 0. So a would actually be a 1, the b, since there's not a linear term, the coefficient was a 0, and c would equal the -9. So g, we have x squared plus 3x equals 5x. So notice how I have to bring the 5x over, but notice how there's already a linear term over there. So this one, it may not be better to go ahead and show the work of subtracting a 3x on both sides, because we do have to combine some like terms together. So we end up with then is this x squared. Just got running out of room. So x squared. That don't look right. Let's try this again. Something just doesn't look right. So again, we want to set the right-hand side equal to 0. So we want to subtract a 5x to both sides. We want to get everything on the same side as the quadratic term. So we have this, the x squared comes down, the 3x and the -5x comes together to give me a -2x is equal to then a 0. Since the 5x and -5x will 0 out. So that means our a is actually going to equal 1, our b is going to equal -2, and since there's not a constant present, that's going to equal 0. Let's see what we got next here. So let's try to do h as well here. So I have a 7 minus x squared equals 3 plus x. So again, we can move everything to the same side as the quadratic term. There's all kinds of ways to do this. Just depends on what you're doing it. So there could be more than one answer to this one, because there's a lot of things that got to move. So the first thing I would probably pick up on is I'd rather have this as -x squared plus 7 is equal to like x plus 3, putting things in the correct order. But I still got to move the x and the 3 over their side. So I want to subtract an x, and I want to subtract a 3, and I want to subtract an x, and I want to subtract a 3 to both sides. In doing so, what we pick up on is you still have this -x squared. The -x would drop into the problem because it doesn't have a like term. But the 7 plus -3 have to be put together. That's going to be a +4, and then that's going to equal a 0. So if you left it in this form, you could say a equals -1, b is equal to a -1, and c is equal to a 4. Now you could also had x squared plus x minus 4 is equal to 0. If you had things flipped over to the other side of the equation, you could add x squared plus x plus or minus 4 is equal to 0, because so you also could add a equals 1, b equals 1, and c equals -4. That could be another choice. So there can be more than one answer for both of those. There's not a really hard and fast rule for quadratics in that sense. So there could be different ways of writing it. So let's get into actually solving quadratic equations. So remember, if I gave you like an equation like 2x plus 6 is equal to 0, this is considered a linear equation. We're just trying to get x by itself. So we would subtract 6 on both sides. This would give us then 2x equals -6. And then if I divide both sides by 2 to make the coefficient 1, we end up with x equals -3. So let's set a linear equation. There was one solution. What we're going to pick up on with quadratics, so in other words, if I give you x squared is equal to, say, 9 as an example, notice that this answer could be a positive or a -3. There's actually two solutions here, because 3 squared gives me 9 and -3 squared gives me 9. So a quadratic equation can have up to 2 different answers. So we got to keep that in mind as we move forward. So now let's get into, solving a pure quadratic equation. So remember, a pure quadratic equation has the quadratic term and the constant present. What's missing is the linear term. So one of the things it says, rearrange the equation if necessary, so that the quadratic term is on one side of the equation and the constant's on the other side of the equation. So let's look at this first example. We have this 3y squared equals 27. is the quadratic term on one side of the equation is the constant on the other side of the equation? Yeah, that's what they're looking for. So step one, if necessary, well, it wasn't necessary for this one. So again, there's no like terms. If you look at the left side, it's simplified, and the right side is simplified. So step two, there's no like terms. Step three says rewrite the equation so that the quadratic term has a coefficient of a positive 1. Notice right now the coefficient of the quadratic term is a 3. So to get rid of the 3, we need to divide by 3 to create a coefficient of 1. So when the 3's divide out, the coefficient becomes a 1, so we don't have to write it anymore. And 27 divided by 3 is going to be then this 9. So we've done that now. Step 3 is make sure the quadratic term has a coefficient of 1. Check. So apply the square root property of equality by taking the square root of both sides. So remember, the inverse of squaring is what's called the square root. So if I take the square of this side, I got to take the square of this side. But I got to remember, though, that this is going to be a plus or minus situation because you could have a positive or negative. So when I do that, I got to remember to put a plus or minus there because it can be a positive or negative. So the square root of y squared does just become y. And the square root of 9 would be a 3. And we'd end up with this plus or minus 3 as a solution. Again, if I want to check it, I can. 3 times 3 squared, does that equal 27? 3 times 9, does that equal 27? Yeah, 27 does equal 27. That does check. If I check it with a negative 3, 3 times negative 3 squared equals 27. That would be 3 times 9 again equals 27 because a negative times a negative is a positive. 27 does equal 27, so it does check out. So both those numbers do work. So there are actually two solutions to this equation. So if we look at example 4, notice that this is a pure quadratic equation. If it's a pure quadratic equation, we want to get the quadratic term on one side and the constant on the other side of the equation. So we add a 9 to both sides or just move it over. We end up with this 4x squared is equal to this 9. So the next step is make sure the coefficient of the quadratic term is a 1. So we have to divide this side by 4 as long as we decide to divide the other side by 4. So that's how the 4's will divide out. X squared does equal then this 9/4. Now this is where to get the x on one side, we have to use the square root property. So we have to take the square root of both sides. And when we do that though, this has got to remember to be a plus or minus situation. So this becomes then x. And this is going to be the plus or minus the square root of 9 over the square root of 4. So the square root of 9 is actually a 3, and the square root of 4 is actually a 2. So x equals a plus or minus 3/2 will be our solution. So getting into 15.2, we'll stop for a second.